In this video, we're going to go over integrated rate laws. So thinking back to rate laws, the question we were asking was, how does rate depend on concentration? So for the simple reaction of A going to B, for our zero order reaction, rate is just equal to the rate constant K. For our first order, rate was equal to K times the concentration of A, our reactant, and for second order, the rate was equal to K times the concentration of our reactant squared. So for a zeroth order reaction, the rate does not depend on concentration. For first order, it's a linear relationship, and for second order, it's quadratic. Now for integrated rate laws, the question we're asking is, how does concentration change with time? So let's look again at our simple reaction of A going to B. If we make a graph of time versus the concentration of our reactant A, we have to start with some concentration on the y-axis, and then after some amount of time, a certain amount of that reactant will be used up. So the question that we're asking with integrated rate laws is, how does it change? So for example, does it go in a straight line? Maybe it starts using a little bit more of the reactant at the beginning and then it slows down, or maybe it reacts really quickly at the start and then it slows down and moves to the end position. And so our equations for this, if we have a zero order reaction, we say that the concentration of our reactant at time t is equal to negative Kt plus the concentration at time 0. So K is the rate constant and T is our time on the x-axis. For a first order reaction, our equation is the natural log of the concentration of A at time t is equal to negative Kt plus the natural log of the starting concentration. And for our second order reaction, we have an inverse relationship. So 1 over the concentration at time t is equal to Kt, and here our rate constant is positive, plus 1 over the starting concentration. And what we can notice about all three of these equations is that they're in the format y is equal to mx plus b, where x is our time. And what we can notice from this is that if we were to graph for example, the zeroth order equation, if we graphed the concentration on the y-axis and time on the x-axis, we would get a linear relationship. For first order, if we graphed the natural log versus time, we would get a linear relationship. And for second order, if we graphed 1 over the concentration versus time, we would also get a linear relationship. So let's see how these are used. So let's say that we were given these three graphs for the reaction of A decomposing into B and C. And let's say we were asked to determine the reaction order. So what we want to look at when we're given graphs is the axes. So we see this graph furthest on the left, and our y-axis is the concentration of A with respect to time. And so if that's our y value, since it's on our y-axis, we can match that to our integrated rate law equation, which is the zeroth order equation. And our equation there is negative Kt plus the concentration initially. And what we notice here is that the line is not linear, so since our equation is in the y equals mx plus b form, we're expecting a linear graph. So since it's not linear, we know that it's not a zeroth order reaction. Now for the second graph, we have the natural log of A on our y-axis, and so that matches our first order reaction integrated rate law. And here we notice that the graph is linear, so it matches our y equals mx plus b format. So from that we can conclude that this is first order with respect to our reactant A. Now here's a second set of graphs. So pause the video to try to figure out what order this reaction is. So what we're looking for here is we're looking for the linear graph. So it looks like the last graph has a positive linear slope. So if we look at the y-axis, we see that it's 1 over the concentration of A with respect to time. So that matches our second order equation, which is kT plus 1 over the concentration of A initially. And what we notice here is that there's no negative sign in front of the K, so K is positive, and therefore with second order reactions we would expect our slope to be positive, which is what we see in this graph. So that confirms that this would be a second order reaction. Now let's do an example of the applications of our equations. So we're given that this reaction exhibits first order kinetics, and the initial concentration is 0.150 molar, and we're given a rate constant. So we know that it's first order, so the equation that we'll want to be using is the natural log of the concentration of our reactant at time t, and that's equal to negative kT plus the natural log of our initial concentration. And we know that what we're trying to solve for is our concentration at a given time, which is 2 minutes. So let's start by plugging in what we know. So the rate constant is 5.3 times 10 to the negative third seconds to the minus 1. And the time, since our unit here is in seconds, we have to match our time to those units so that they cancel out. So we're given 2 minutes, and so there's 120 seconds in 2 minutes. So our time is 120. And then we evaluate the natural log at our initial concentration of 0.150 molar. So if we plug this into our calculator, we should be able to simplify it to negative 0.636 plus negative 1.897. And so that can be simplified further to negative 2.533. And then we need to cancel out our natural log to solve for the concentration. So if we remember, we can cancel out natural logs by using our e. So if we raise both sides, or if we have e raised to the power of both sides, the e and the natural log will cancel out. And then we can evaluate e to the negative 2.533. So if we do that, we should get the concentration of CH3 CH2Cl is equal to 0.0794 molar at time is equal to 2 minutes. Let's do another example. So here we're given the decomposition of hydrogen peroxide, and we're given a rate constant and the concentration at time of 1 hour. So here we're not given the reaction order. But a unique thing about the rate constants is that based on the units of our rate constant, we can determine the reaction order. So if we think of our rates, for example, our 0th order, the rate is equal to K. And since we know that rates always have units of molarity per second, that means the K value must also have units of molarity per second. So for a first order reaction, our rate is equal to K times the concentration of our reactant. So again, rate is molarity per second. but now we're multiplying by the concentration of A, which has units of molarity. So now, in order to get a final rate unit of molarity per second, our rate constant K must have units of 1 over seconds, so that they multiply to molarity per second. For a second order, our rate is equal to K times the concentration of A squared. So now to get our final units of molarity per second, we're multiplying by molarity squared. So we need 1 over molarity times seconds. And so 1 over molarity times seconds is equal to molarity to the negative first, seconds to the negative first. So based on our units, this reaction must be second order. So now you can take a moment to try to solve it on your own. So now that we know the reaction is second order, the equation that we'll want to be using is 1 over the concentration of hydrogen peroxide evaluated at the time of 1 hour, and that's equal to Kt plus 1 over the initial concentration. And here we're trying to solve for that initial concentration. So let's plug in what we know. So our initial concentration is 0.182. Our rate constant is 1.25 times 10 to the negative second. And let's keep our units in here. And our time is 1 hour. So 1 hour is equal to 60 seconds per minute times 60 minutes in an hour. So that should be 3,600 seconds in an hour. And then we can add what we're trying to solve for. Then we can move this to the left side of our equation to get 1 over 0.182 molar is equal to 1.25 times 10 to the negative second times 3,600, and that should be a minus sign, is equal to 1 over the concentration of H2O2 at our initial time. Then we can plug this into our calculator, and the left side should give us 0.995 molarity to the negative first is equal to, and we have seconds here, so our seconds cancel, is equal to 1 over the concentration of H2O2 at time 0. Then we take the inverse of this, and we get that our initial concentration is equal to 1.01 molar with 3 significant figures. In this last example, we're given the decomposition of N2O5 to NO2 and oxygen with first order kinetics. So we know the equation we're going to be using is the natural log of N2O5 at time t is equal to negative Kt plus the natural log of N2O5 initial. And so we're given the initial concentration, and we're given the final concentration, and we're given a time of 10 minutes. So let's plug in everything that we know. So the natural log of 0.184 is equal to negative K times 10 minutes plus the natural log of our initial concentration. And so we can rearrange this by moving our natural log to the other side. And then dividing by the 10 minutes. And that will equal negative K. Then if we plug all of this into our calculator, we get negative 0.0307 is equal to negative k. And our negative signs will cancel out, so k is equal to 0.0307. And for our units here, we have minutes for our time, so our units will be minutes to the negative first. Next, we're asked to find the concentration of our product, NO2, at time is equal to 10 minutes. So let's think about what's happening here. We're starting with 0.25 molar of our reactant, and our reactant concentrations are decreasing. And we're not starting with any of our products. So whatever started as our reactant has progressed through the reaction to become our product. So if we started with 0.250 molar of our reactant, and then at the end we had 0.184 molar of our reactant, that means that we produced 0.66 molar of our products. But we have a stoichiometry here. So we have a 1 on our reactant side and a 2 on our product side. So for every 1 mole of reactant, we get 2 moles of products. So therefore, we have to multiply our answer by 2, by our stoichiometry. So 2 NO2s for every 1 N2O5. And that'll give us a final answer of 1.32 molar NO2 produced in our reaction after 10 minutes.